Hello, Saddleback College Robotics is proud to present our 6th generation rover, Ares. Our team is organized into 4 sub-teams: mechanical, electrical, programming, and science. Our chassis is constructed of welded aluminum tubing with removable panels to protect interior components. The chassis features a machined belly pan capable of housing electronics in numerous configurations. Ares is powered by 2 24-volt batteries connected in parallel, enabling extremely long runtimes. The drive system is built around a custom control arm suspension with adjustable pneumatic shocks, providing resilience during missions across rough terrain. Ares' 14-inch 3D printed wheels, paired with custom wheel hubs and bearing blocks, balance durability and flexibility while maintaining a low weight.
The electrical system on Ares features many advances in organization and design. A custom PCB handles the switching of our analog video feeds, while another controls the motors and sensors on our science system. Within the rover chassis, our custom power distribution board controls power with a mechanical relay and is able to supply different voltage rails with fuse protection and current monitoring capabilities. Robust communication across hardware devices is achieved by using CAN bus, and organized wiring harnesses greatly simplify hardware assembly and maintenance. In an emergency, pressing the accessible kill switch disconnects the battery and shuts off all power.
Ares' completely revamped 6 degree of freedom arm implements brushless motors for high torque density. The first 3 axes of the arm comprise strain wave gearboxes for minimum backlash on high load joints. The final 3 axes use custom cycloidal gearboxes for high torque and zero backdrivability. Relative and absolute encoding on every axis allows precise inverse kinematics for ease of operation. Rigid aluminum tubing allows the arm to easily lift loads of 5 kilograms. With our new mission-equivalent rocket ship, the arm has been tested for fine movements. Our lead screw-driven end effector features textured neoprene grips to securely pick up objects, operate joysticks, flip switches, and open cabinets and drawers. It houses a small linear actuator for precisely pressing buttons and a hex key for tightening screws. 4 unique camera views give operators great spatial awareness.
Communication with the rover utilizes a point-to-point wireless network bridge running on a 2.4 GHz radio band. ROS2 is used as a communication framework to enable the control of systems on board the rover, as well as to facilitate the transmission of telemetry back to base station. The startup and shutdown of individual subsystems, as well as the control of the science subsystem, is operated by a custom-designed web interface. Manual control of the arm and drive system utilizes separate gamepad controllers to provide better handling of each individual subsystem.
Autonomous navigation is achieved through the use of the ROS2 navigation stack, processed on NVIDIA Jetson Orin.
Precise localization is achieved through a sensor fusion approach consisting of input from wheel encoders, visual inertial odometry, and high-precision GNSS positioning and heading, augmented by real-time kinematics. The navigation server uses fused odometry estimates as well as obstacle data provided by LiDAR and stereo camera point clouds to generate a cost map. Safe trajectories are then planned around identified obstacles using the A-star algorithm, and velocity commands are output to the rover's drive system. Operators at base station can set GNSS waypoints via point and click on an interactive map using the ROS2 MapFizz package.
A stereo camera paired with our custom-trained convolutional neural network enables the detection of specific objects such as water bottles and mallets. This capability is bolstered by an augmented dataset that enhances recognition accuracy. Additionally, a dedicated ROS package enables the detection of Uruko tags and outputs their relative coordinates. If commanded to search for an object or tag, the rover will perform a spiral search upon arrival at its target GNSS waypoint. The rover then sets a new waypoint near a detected object's position and on arrival notifies the operators.
Our science mission is equipped with a deployable platform designed to detect evidence of extinct and extant life in sites of interest. The payload houses a series of scoops that enable the collection of multiple samples per site, as well as preventing cross-site contamination. Through NDIR spectroscopy, metabolic responses from added substrates, such as CO2 gas, can be detected, and their biological origin can be determined. Similarly, we will search for vestiges of past life, such as biotic synthesis of carbonates and biomineralization from gaseous HCl reaction products. Additionally, our payload boasts a returnable sample collection system with a drilling canister, enabling precise subsurface sampling below 10 centimeters. Our team has pioneered an approach for rapid identification of habitable landscapes for site selection, from geological measurements extracted from images captured by our Mastcam.